Okay, welcome. It's very appreciated that you came on this bad weather and in the first day of the year. Quite a few of you. Cool. Okay. So, welcome to this. I think we're on the ninth lecture, or yeah, I think so. This is so. Last week we talked about snapshots and on-the-fly mark sweep collection, and today we want to do reference counting. Um, so we'll start with the basic reference counting. We'll then do some simple improvements, and then we'll talk why reference counting was not used for many years and why it was considered not so good. And then we'll see improvements from 20 years ago that made it available for today's machines and platforms. Okay. So it started in 1960, like Mark Swift. So, and the basic idea is that you have a reference count for each object, telling you how many references reference it. And so when nothing points to the object, the reference count is zero. You can reclaim it. It's clearly unreachable. So the basic thing that happens is that if you modify, so in the beginning, an object would get reference count 1, and then whenever a pointer is modified, we let the reference count of the object that lost a reference decrement by 1, and increment the reference count of the object that obtained the reference in this single modification of a pointer. So we do these two, and then if this was the last pointer, so the reference count becomes 0, then we can reclaim it. And what we should notice is that if we reclaim it, then all its children lose a reference count. So this should be, so we decrement so we delete it, we return it to the allocator, and then we decrement the reference counts for all its descendants. And this could become recursive because if one of them becomes 0, then we have to delete it and then decrement for all its children and so forth. So this is the basic method, and from 1960, and 3 years later, it was noticed that it doesn't reclaim cycles. And it's not because people were less smart in these days that it took 3 years. It was just not used very much. And so people did not care too much. And so after 3 years, there was this paper saying that you cannot reclaim cycles. Cycles meaning strongly connected components. You will never see the reference counts of any of the objects there decremented to 0 if it's not reachable and the program does not modify it. Okay, but typical programs do not use too many cyclic structures. This is what they said then. It's still true today. So you know, if you look at most of the modern benchmarks, they don't use any cyclic structures. There is like you know, Java C is a benchmark. It's a Java compiler. It does use a doubly linked list, which is a cyclic structure for representing code. And so for that, you would have a problem, but most programs do not use it. So other methods, we could once in a while run mark sweep. Mark sweep does not care if the reclaimed objects are in cycles or not. It never touches the reclaimed objects. It just traverses everything that's reachable from the roots. The rest could be anything, could be cycles, could be whatever you want. It's just reclaimed in sweep because it's not marked. And so so you could use mark sweep to reclaim cycles infrequently. Why is reference counting good? So initially with naive algorithm, it's a very simple implementation. You just have to increment, decrement, and reclaim whatever goes to 0. And there is an immediate reuse, which is really good. So if something gets to zero, becomes garbage, you immediately, just when the pointer changes, it loses the last pointer and you reclaim it immediately. And so if it's not in a cycle, and then you can use it again. So there is there is this space that is reused immediately when it's not needed anymore, and that's good for locality. So you always use the same space to work with, and overheads are distributed through the time of the computation because each time if there's no, so you could lose a pointer to a big structure and then recursively reclaim it all, but normally you lose a pointer to like an object or two that become garbage, and then your work is distributed. Each time you reclaim an object, you give it to the allocator and you go on executing. So you get the overheads are not noticeable almost all the time. So these were good properties for the naive algorithms. We'll see that today's algorithms are not like that, but that was initially. Today, so I think if you compare reference counting to mark sweep, what happens with mark sweep is that mark sweep goes through the entire space that you're using to just mark all the reachable objects. And so mark sweep, if you're using a substantial structure, it will cost a lot for each garbage collection. And reference counting is proportional to how much work you do, how many objects you reclaim. It just goes through the objects you want to reclaim and reclaims them. And so and also when you change a pointer, you have to do some work to update the reference count. So it's proportional to the amount of work that you do and not to how many objects you keep. And you could think of it as reference counting is like you pay for what you actually do, and in tracing it's like a property tax. You pay for what you have. So if garbage collection is frequent, and you have to collect a lot of times, then tracing will be terrible because each time you try to reclaim objects, you have to trace the entire space that you occupy. And with reference counting, you just pay for the changes you make and for the objects that you reclaim. And so in today's world, sometimes there are occasions where you really are doing a lot of garbage collection. So for example, even in machine learning, you have models and you want them to be as large as possible because they do better work in predicting. And so you want them to capture much of your memory, and then only a bit is left for other allocations. And then you allocate a bit and then you reclaim. And now when you reclaim, you don't want to go through your entire space. You want to just pay for the little work that you did before before you needed to reclaim again. And so in modern uses, sometimes you collect many times. And in these cases, reference counting will do a lot better than tracing. And we want to be able to work with reference counting to understand it. And there are attempts to put it into modern systems today. Yeah. Right. Right. So think when you have like space like a heap, and you have the amount of space that you actually use. Okay. And then if you leave a small space, if you're willing to work with something like that, which was supposed to be good in the past, so you use half of the heap and then you allocate until you finish, and then you reclaim. And in this scenario, it's good to it's okay to have mark sweep, but if you really want to have maybe the largest model you can put in the memory in order to predict better, and you just worry about space, you're not willing to give up half of the space, then what will happen is that you allocate a bit and then you'll need to do garbage collection. And you don't want to trace all of these large spaces that you keep. You want just to pay for the work that you did in between. So you pay for modified pointers, you pay for the objects that you reclaim. And so it's a lot better to do reference counting when you're in a situation like that. You really want to use your memory. You don't want to leave a lot of space for allocation. Yeah, so these are today in more complex algorithms. We'll talk about that. So you will not do it all the time. Yeah, it will not be immediate reclamation. Yeah, good question. Yeah. Okay, so this is the situation. And so, what is wrong about reference counting? Initially, so think of the overhead. It is terrible. I want to change a pointer. I have to change the pointer and then decrement the reference count and increment the reference count. Maybe I get cache misses because it's all over the heap, but what I'm touching. And the cost of removing a last pointer to an object is unbounded. Maybe you remove the last pointer to a large tree and you're now going to recursively reclaim all the objects in the tree. And then basically you have to work a lot just because you move the pointer. So it's impossible for the programmer to understand what will cause pauses in its work. Space overhead, I need a counter per object. So for each object, I need to know how many pointers are referencing it. Maybe the entire heap is just referencing, a single object. So I have to leave space for the number of pointers that could be in the heap. And that is a word of, and so I need to keep this for each object. I cannot reclaim strongly connected components, so this is also a problem, and it's difficult to parallelize. I will talk about it later. And so, it was not so good. And today, everything is fine. The reclaiming cyclic data structures is still a struggle, and we'll talk about that next week. Okay, so let's go through some basic ideas how to improve naive reference counting. And these ideas are mostly from the 60s, 70s maybe. And then we'll jump to 2000 where we had some more breakthroughs or jumps in the understanding of these algorithms. Okay, so this is the list. Let's start with the first one. So the first one said, you have this problem that sometimes you move a pointer and you have to reclaim lots of objects, and that will take a lot of time. So I want it to be more smooth. I don't want to have jumps and differences in the costs of moving pointers. So, like, many times in computer science, we'll do lazy freeing. We can do stuff lazily, so we don't need to reclaim all this space. What we can do is, reclaim maybe the first object, and next time we need to allocate, we'll reclaim the next one, and so forth. Whenever we need to allocate, we'll reclaim something. But we have to maintain correctness and the ability to reclaim all of them. So what we'll do whenever we have a reference count going to zero, we'll push the object to a stack that we designate for that. And during allocation, if I need an object, I will pop an object from the stack. This is an object that should be reclaimed. I can use it. I will free it, and I will decrement the reference count for all its children. If any of its children reaches zero reference count, I will push it to the stack. So it will be treated, later, lazily. Yeah. Okay. Right. So, first of all, I do it all the time. This was suggested for Lisp in the 60s, and in Lisp all objects are of size 2. So it's always okay to just take something from the stack and use it. So this was good in the sense that today you may think maybe I pop an object and it's just too small and I cannot use it. But in those days it was really easy. The stack could get longer if it gets too big. Then I can just stop everything and just process it. Do the reference counts for everybody, reclaim it, and finish it. So I can check that I'm not going too large. Yeah, but I'm doing it whenever I need to allocate an object. You could go in between. You could say when I allocate an object, I process 4 elements in the stack and so forth. Okay. So the properties, I split the cost of deletions evenly through the computation. And the overall efficiency is almost unchanged because I do the same work. I just go through the stack when I do that. The disadvantage is that it complicates the allocation process. So if I need a large object, it's not Lisp, and I really need a large object, I need to free many small objects in order to find space for allocation, then it may take time. That's the efficiency. So this is like the first method that people suggested to improve reference counting. And if you have questions, let's go to the second one. The second one is very much used today. We don't want, so the problem is that we need like a word for each object to maintain the reference count, and we don't want to keep so much space wasted. And theoretically, it should be large enough to hold the number of pointers in the heap. So it has to be of the size of a pointer. But the idea is that most objects do not really have a large reference count. So if you look at benchmarks today, about 80% of the objects just have a single reference. And so the reference count is 1. And 15% more will have, like 95% of the objects will have less than 2 pointers pointing to them. So we really could work, most of the time we'll have a small number in the reference count. So we could use a small reference count field, which may overflow for some objects, surely not for all, but some objects could overflow. And then we could think of it as stack. So suppose I use 4 bits for the reference count. So the reference counts could only go as high as 15. And when it gets to 15, for me, it's stuck. I don't know, so I cannot move it up. And I don't know if if I attempted to increment it in the past, so I cannot decrement it. Maybe it's now 19, and all I have in my field is 15. So I cannot decrement it when it loses a pointer. So I just call it stuck, and I don't execute any decrements or increments. And if I want to reclaim an object, so maybe it was stuck and after a long while, it lost all pointers and returned to 0 or to 2, and I could restore it and keep it within my 4 bits, but I have to do something to restore the reference count, and I could do it with the tracing collector. Okay, so the problem is clear, the solution is clear, and the drawbacks are clear. Okay, cool. So here is how I restore reference count with a mark sweep. I could start a mark sweep by clearing all the reference counts in the system. And then for each pointer in the roots, I call mark, and this will be a recursive operation. And then I resweep. So what does mark that? Mark has to restore all the reference counts. And so it has to work with reference count. So what it does it, for each pointer, it will be called, and then I want to increment the reference count of the referenced object for each pointer. Now, for the first time I see an object, it is incremented from 0 to 1, then I want to also look at its children. So if I incremented it and it became 1, then I will go for the children, and recursively, this is a pointer that I'm looking at, and I'm going to increment the child's reference count. And if it's the first time I'm visiting the child, I will visit its children, and so forth. So I'm currently marking all the, it's not the program, it's me as the collector. I'm doing the mark sweep. The program does change pointers and it has children. But the collector is now traversing the entire live object. When it sees the object the first time, it will visit all its children. But in the next times it visits the object through other pointers, it will see that the reference count is above 1, and then it will not go on visiting the children. So you could think of it as a mark. So if it's 0, it's unmarked, and if it's 1 or above, it's marked, and I will not go to traverse its children. But I also get the reference count restored, and maybe if I increment the reference count enough, it will be stuck again, and it's okay because it's above my 15 limit, and it should be stuck. But if it was, it became 3 and I couldn't change the 15 because it was stuck, then when I do the mark sweep, I will discover that it's 3 and I can work with it until it may get stuck again or may go down to 0, and then I can reclaim it. Yeah. Right. If some object reference count was stuck and some time has passed and I want to see if maybe its reference count was decreased to a lower level, I will run mark sweep. I will wait until many objects are stuck, and then I will do this. And some of them will go down to 0, and then I can reclaim them. Some of them will go down to maybe 3, and then I will be able to follow the reference count. Okay. So here is the statistics. Most objects have unique references, which is around 85%. And so there was a paper that said, let's just use 1 bit for the reference count. And this will say, if the bit is 0, then it's a unique reference. And if it's 1, there is more than 1 reference to the object. And if it goes below unique, like it has no references, it will be like -1, but I will immediately reclaim it and it will not be in the heap anymore. So this is like 1 bit will suffice to see if there is a unique reference or not, or many references. And so the simple implementation is to have a bit per object, which says if it's uniquely pointed or shared by several pointers. And I could improve the implementation. This was suggested later by looking at putting the bit in the pointer. So in the pointer, I could say this is a unique pointer to this object. And whenever I do an assignment, and for example, I want to put this here, then I will change it to shared. So when I create the first pointer, when the object is allocated, I will put a unique on the pointer to it. And whenever it's copied somewhere else, I will make the original share and the copied pointer shared. And so I will be able to tell if a pointer, if I lose a unique pointer, then I know I can reclaim the object, right? If this is changed or just destroyed, moved to null, then I know this can be reclaimed. If it becomes shared, it's stuck and I cannot reclaim it. Yeah. Right. So if I lose this one, this could become unique again, right? But it's like a stuck pointer. It went up to 15 and I don't decrement or increment it. It remains shared. It will be only 1 pointer, but it will be marked as shared. Only if I do a mark sweep again, I will be able to get back to unique for this object. That's correct. What's good about this is that when I change the pointer, I don't need to access this object. Normally, when I want to change the reference count, I have to go to the referent and I have to change the reference count for it. But here, I just touch these pointers and I change it in the pointers. It's from locality point of view, I suffer less cache misses because I just touch the pointers. I don't touch the children of these pointers. Okay, so this is okay, and so this is it. And another thing that is done with stock reference count with small field reference count is that sometimes we want to use a software cache. So, for example, think of me going over a linked list, like I'm starting for the head and going over all the pointers. And when I'm visiting an object, I'm incrementing its reference count. And maybe I'm getting it stuck because I just visit it for a short while and then I go on. And the software cache is meant to not get all these stuck on the way just because I go visiting them. So so if I go over a linked list, I may increment the reference count and get it stuck. And the software cache says, let's keep a list, a cache, of the most recent objects that I incremented the reference count and became stuck. So all these objects, if I manage to decrement the reference count before I get them out of the cache, so maybe the cache is not large enough and I need to remove someone before it's decremented. And then it's stuck and I cannot do anything with it. But sometimes I will be able, like if I'm going through this linked list, someone enters this cache and then immediately its reference count is decremented, then I can get it out of the cache because it's not overflowed anymore. It's not stuck. So if an RC is decremented before leaving the cache, then it can be updated and removed from the cache. Yeah. Right, I could do it also with many bits. So it's like, right. So forget about the other optimization. Just say that we have even one bit. Yes, let's say this is like I'm going over this linked list. Okay, and whenever I go through the next one, it gets stuck because it's shared. It gets from 0 to 1, and I cannot touch it anymore. Now, if instead of going to 1 for say this one, I'm saying I don't know, this is object A. They have addresses, they don't have letters. But suppose in the cache I say object A got to 2 pointers, right? Shared, and then it could go up to 3 and 4. Here I have space, like this is a word of the reference count, this is a word for the address. I don't have limitations because I'm keeping just a small table. And this is my cache. And so A could, incremented a lot, decremented a lot. But if it goes down to 1 again, I can take it out of the cache and say it's not overflowed. But sometimes, the cache is not enough and I have to put someone here and take someone out. And if that gets out, then it's stuck. I will not know how to decrement it later. Okay. This is like a standard method. You use sometimes a software cache in order to solve temporary issues that you have. And, yeah, so this is the way it works. More questions? Okay, so now we go into something more serious, which, I mean, stock reference count, like limited field reference counts, is used everywhere also today. Deferred reference counting is a bit more involved, and it's also used everywhere if someone wants to use reference counting. So the problem is that we have a write barrier on the roots. So whenever we change a local pointer, we need to just, suppose we're going over this linked list and we're just reading each object and going to the next one, we have to increment the reference count of this guy. Then when we go to that, we increment the decrement. So for each move in this linked list, we do 2 writes of reference counts updates. And so this is not good. This is a lot of overhead. And this is an overhead on updating the program variables, the roots. So like if I have this pointer and I'm just changing it to move from one object to another, it's going to be very costly. So this is a problem, and the way that deferred reference counting suggested to solve it is in 1976, Deutsch and Bobrow. It's called deferred reference counting, and so we just don't update the reference count when the roots are modified. So we have no monitoring of the roots. We just let them run without a write barrier. And now the reference count only reflect the reference count inside the heap, not from the roots. So if I have if I have a heap, right? And I have an object pointing to another, and then from the roots I have pointers to both of them. The reference counts are going to only reflect, this is going to be 0, and this is going to be 1. The roots pointers are not going to be monitored, they're not going to be reflected in the reference counts. So the reference counts are smaller than they actually are because they don't consider roots. So because I don't want to monitor the roots. Roots change a lot, like all the time. In your program, you write p equals p dot head, dot next, and you just go over the list, and you change your local pointers all the time. If you try to monitor that, and for each time you change it, you do 2 more writes to increment and decrement reference counts, it's going to be very costly. This would make it, unacceptable for reasonable modern collectors. Yes, it happens very, very often. All the other collectors that we did with write barriers, we always excluded write barriers on roots. There were no write barriers on roots. It costed us some complication in the collectors, but it has to be like that. Otherwise, they're changing too often, and you don't want to put work into it. And here, it's more expensive than the write barriers we've seen before, because you have like increment and decrement instead of maybe writing a bit somewhere to mark somewhere or to gray someone. You really are doing a lot of work. So we have to remove that, and so you now objects that so the implication of this is then when you see a reference count goes down to 0, you cannot reclaim it because maybe it's referenced by the roots, and then you cannot reclaim it. So objects with the reference count 0 are recorded. You say, this one went down to 0. I don't know if it can be reclaimed, but I put it in some list. It's called the 0 count table. That's how they called it. And once in a while, and now we're getting back to non-immediate reclamation, like we had in Mark Sweep. Once in a while, we do a garbage collection and we check whether these objects that we put in the 0 count table are really not referenced by the roots. So I go over all the objects in the 0 count table, and those that are not referenced by the roots, I can reclaim. This is, yeah. Right. Okay. So let's look at the code. If I decrement a reference count and then I discover that it's 0, I just add it to the 0 count table. I don't reclaim it. And when I update a pointer, I increment the reference count of the new target. I delete this way the old value of the reference. And I could remove, like you say, the new one from the ZCT. So if I'm going to point to someone, it doesn't have to be in the ZCT anymore. This has a cost. It gets into, this is the right barrier, and it goes throughout the execution of the program. You add some cost to the right barrier. Usually we prefer to do it in the time of the collection. That happens, infrequently, and we don't want to burden. So we could do this, but usually we prefer not to. So this would be the right when I want to collect the way. Yeah.
Do we solve samples this way? Because
No.
you're only deleting whatever's not.
Right. Cycles we cannot reclaim. Next week we'll talk about cycles. This will be the challenge. Right. Definitely. So the collector that happens once in a while, what it does is that first of all it increments all the references from the roots. It increments the reference count. So after doing that, I know that the reference counts are correct. They also account for all these references, and then I go over all the ZCT, all those that I saw were zero. And if they're still zero with the increments from the roots, then they're really unreachable, both from the heap and also from the local pointers. And then I should delete them. So I first delete their children, and then I reclaim them. And after when I finish the garbage collection, I go back and decrement the reference from the root, so it will be still reflect only pointers from the root, from the heap. Okay, makes sense. So this is deferred reference counting. New objects. So when you do a malloc or a new, usually you get a reference from the roots. You get a local pointer to the new object. And since local pointers are not do not count for the reference counts, we just give it a reference count 0, but we have to put them in the ZCT because they have a reference count 0, and they are only a reference from the roots, new object. So this is how new objects are treated. Properties, it reduces overhead, and they measured 80%, so it was reduced by a factor of 5. So this is really important to use it if you do reference counting. And the disadvantages is you don't collect immediately anymore. So you remember you asked about immediate. This is, with this, which you have to use, you don't have immediacy anymore. And also you have some space overhead for the zero count table. You can control it because you can say if it's too large, I can just stop and do a garbage collection, and then I can reduce it. But it's really frequently used. It's very important. Yeah. Definitely, it does harm locality. On the other hand, there is something good still about locality is that in Mark Sweep, you go over all the live objects. You don't really touch the non-live objects, and then you start working, you allocate the non-live objects, the unreachable, dead objects. And here, you just touch the dead objects, which are going to be allocated and used afterwards. So this is still considered better in terms of locality, but not as good as it was with the immediate reference counting. So this is the deferred reference counting. Okay, so why did people not use reference count for, between the 60s and until the 2000s for many, many years? So first of all, it doesn't reclaim cycles, which we need to get Mark Sweep to reclaim the cycles or some algorithms we'll talk next week. This is still a problem, but we'll talk about it next week. The second thing is this, you have a heavy overhead on pointer modifications. Even if you do it just for changing pointers in the heap, the right barrier is going to be a lot more costly than write barriers of mark sweep. This is really costly that you have to increment that and decrement that. You may get a cache miss. It's a problem. It's a lot of overhead, and and then there was a traditional belief that it cannot be used efficiently with parallel processing. So you don't want to use locks whenever you change. And I'm going to talk about this a bit more now. Um, but you will have to use a lock or a compare and swap for each pointer update. You cannot update pointers without basic lockings, which is a problem. And so let's talk a bit about that. So you agree that it's a heavy write barrier, like it's not what we studied in the past, dirty cards, you just write a dirty bit somewhere. Here you have to go somewhere, increment a reference count, decrement a reference count. It's very high. And now let's talk about concurrency. So first of all, the reference count updates must be atomic. Two threads are incrementing or decrementing the same field. You have to use some lock or compare and swap. That's a problem. You don't want to use a compare and swap in your write barrier because it's expensive. It's not like a regular write. But for that, we have a solution. And each thread just doesn't update the reference count. It just says somewhere, it gives instructions. I want to increment the reference count of that address. I want to decrement the reference count of that address. Now, we don't all the time reclaim objects. We have specific times where we do a garbage collection, and then we just take all the instructions of the threads that were given before we collected, before we did garbage collection, and we just execute them. So each thread just logs the required updates in a local buffer. And when the collector wakes up, it applies all the updates during the garbage collection. And the collector is single threaded. So you don't need to do anything that requires synchronization in the write barrier or when you update the reference counts. Okay, so this is solved. Yeah. So it's a local buffer. Each thread just uses its own local buffer, and so it can write privately without synchronization. And the collector just gathers all the local buffers and just executes all the modifications of the reference count. Right. Right now we're not talking about concurrency. Imagine we want concurrency of threads, but the collector just comes, collects all the instructions of updates, it updates all the reference counts, and soon we'll talk about concurrency. You can do it better, but just allowing the threads to work without a very expensive write barrier that takes a lock or does a compare and swap, this will work. Yeah. From now on, we're only in deferred reference counting, yes. Because otherwise it's too expensive. Yeah. Cool. So here's the second more non-obvious problem that, sometimes even experts are not sensitive to. This is a real problem. So what happens here is I cannot tell what the old object is. So look at these two. So there is thread one that tries to write C into A.next, and there is thread two that tries to write D into A.next. And, they work together, and in the real world, one of them happens a bit before the other. So maybe thread one succeeds first to move the pointer from B to C, and then the second threads move it to D. But if you look at the write barrier, what they do, they need to decrement and increment the reference count. So first they read the old value, and both of the old value, and both of them are going to see B as the old value because they act together. And then they write this pointer, one of them writes C, one of them writes D, and maybe D survives, and at the end A points to D. But what we're going to have is two decrements to B's reference count, which is wrong, an increment to C's reference count, which is wrong, and an increment to D's reference count, which is right. So the problem is that this guy doesn't know that it moves the pointer from C to D and not from B to D. And since it doesn't know what the old value is, it's doing a wrong accounting for these reference counts. And so B is going to have a smaller reference count than what it should have, and it may be reclaimed prematurely. And maybe C will never be reclaimed because there is a reference count that's higher by one than the actual pointers that are actually referencing it. So this is a problem, and this is a serious problem. It's a race that happens, and soon you'll have a break. You can think of what you could do with it. Let's before the break, we have a couple of minutes. So I want to jump. There is a third problem which is similar. I want to not describe it here because it's enough that we have one problem. But I want to say there was a first attempt to work with multi-threading and concurrency in 1990 by Det Reville. And he said, of course, we use deferred reference counting. Everybody uses deferred reference counting. We cannot monitor the roots. So we have to give up immediacy and just collect once in a while. And so what he did, and it was a practical system, said, let's lock the heap for each heap pointer modification. If we lock the heap, we don't have this problem that two threads together are trying to modify and they don't know what the old value is. You know exactly the pointer goes from B to A, from A to C. It's clear if you work alone. And you could do, instead of locking the heap, you could do a compare and swap to know what the old value is, but it's the same, it's a high cost. You don't want it. And mutators, as we said before, mutators do not modify the counter. They just write what they want, how they want to modify them. And then the collector updates the reference count. This is how it was done, and it was a lot of overhead. In the write barrier, at the collector, it just reads the buffer. They did global buffer because in any case they used the lock, so it was not a problem additionally. And they just read the buffer, and then it reclaims it applies all the buffers, and then it reclaims objects with reference count 0 that are not referenced by the roots. Okay. And then in 2001, so this is 90, and then 10 years later, there was a work by 5 really serious researchers in IBM in New York, and they did like state-of-the-art reference count for that time. They implemented all the ideas that were known in the papers by then. They also so they did a compare and swap instead of taking the lock, with the same deferred reference counting, of course. And they managed to get on the fly in all kinds of tricks. All the decrements were deferred to the next cycle collections to not create any error in reclaiming objects that are still reachable. They did all kinds of tricks. They got very short pauses. They also suggested the cycle collector, which we'll talk about next week. The problem is still they had this write barrier with high overhead. For each pointer update, I need to do 2 changes of the reference count. And they had a lot of floating garbage because they waited with the decrements to the next collection. And so this was the state at 2001, and it was not good. And you can now think during the break on how to do it a lot better. And we'll meet in 10 minutes. It's 31 we'll meet. So let's see what we want to do. We are working on. We have this high write barrier overhead that seems like, what can you do? You have to update the reference count whenever you change a pointer, right? It seems inherent. How do you get rid of that? And then you have all these braces and problems that you just need to change, to be careful when you change pointers. And that's also like if you do a compare and swap in the right barrier, and the right barrier is already so heavy, it seems like reference counting is doomed. And there was a book, like the previous book on garbage collection. Just if you read it, then just don't use reference counting. And and what Yossi did. So first of all, we use a snapshot as like deferred reference counting. Basically, uses a snapshot, right? It takes all the changes, applies them, and then you have the reference counts for the next snapshot. And then you can work with it to reclaim things with the reference count 0. So what we want is like a new collector with a very light write barrier and no synchronization in it. And that's what we're going to do. And we're going to make it concurrent, and later on the fly, the sliding views methodology. Okay, so how do I reduce overhead? So I have to look at it differently. So when you look at the pointer, it has a parent and a child, right? So usually in reference counting, we just look at the children. They lose reference count, they gain reference counts, but let's look at the parents, and then we get different things. So if you look at I have a pointer, right? And it's going between garbage collections. It's going to point to several objects, to multiple objects, maybe this n+1 object. Oops, let me go back. So it has n+1 objects. It starts with pointing to O0s, then it's going to O1, O2, O3, until it gets to ON in the next garbage collection. Okay, so what would reference counting do for this? So it will do a lot of work. So if you look at it, they will do 2n operations. So I decrement the reference count for this and increment to this, decrement to this, increment to this, decrement, increment, decrement, increment. Yeah. In the original collector, in the deferred reference counting, what you do is you get a list of updates that you have to do, from all the different threads, and you just go one by one and modify it. Yeah. You could do some work by yourself, but you would still need to go through all the instructions and apply them. You could do it more efficiently, but not by a lot. You have like a million, instructions. Basically, you could reduce them, but you have to go over all these millions to do something. Yeah, like this. So if you just look at this pointer, I mean, there's lots of pointers that are changing, but I'm just looking at one because I'm now at the parent view of reference counting. So this guy is going to just go through all these objects, and for it, I'm going to do 2n reference count updates, right? And if you look at it, I only need to do 2, right? So it's a telescopic series, and I increment and decrement the same reference counting, increment and decrement, because when the pointer goes to O1, I increment it, and when it leaves O1, I decrement it. When it goes to O2, I increment it, and then I decrement it. Basically, I just need 2 updates. I need to decrement the reference count of O0 and to increment the reference count of ON. So this is all I need to do. And great. What? Right, I'm not doing anything like between 2 garbage collections. So this is like between 2 garbage collections, right? In the previous garbage collection, it was pointing to O0. In the current garbage collection, it points to ON. I don't care at all to do anything between those 2. I just care when I do the next garbage collection to update all the reference counts so that it will be correct for the current snapshot. That's all I care about. So what I really need to know when I'm doing a garbage collection, I need to know what was it pointing to in the previous snapshot and what it is pointing to in the current snapshot. That's what I really want. And so basically, I have the reference counts update for the previous snapshots, and I want to update them so they will be correct for the current snapshot that I'm now trying to obtain. So we just need to worry about these modified pointers. And for each modified pointer, we have to decrement the reference count for this O0, which it pointed in the previous snapshot, and increment the reference count in to ON, which it points to in the current snapshot. Okay, so the timeline is like this. What I'm going to do is I'm going to, when P, this pointer, first changes, I'm going to record the previous value, this O0, before I write O1 into it, right? And then when it changes again, I have to do nothing, really. I can just go on until the next garbage collection. I don't need to do anything. And then when the garbage collection comes, for each modified pointer like that, I read from the records what was O0, like the value that it had before the first modification. And I can read from the heap now what is ON. And that's enough. So I need to know each modified pointer, what it pointed to in the previous snapshot, in the previous garbage collection. Right. I need the mechanism. I need like buffers. So when a pointer is first, so technically, which is what your excellent question, it leads to the next slide. So when a pointer is first modified, it is marked dirty. Don't know if you remember, we did dirty last time. So, but it's the same. First modified, it becomes dirty, and its previous value is logged. I put it in some buffers that I keep, and I log each object instead of each pointer, and this seems to be the easier way to do it, but modern collectors sometimes log pointers and not objects. But think of it let's talk in objects in this lecture. So what I'm doing is, suppose I have this, I have my local buffer, right? And I'm here and I want to record an object. I'm going to modify an object. I'm going to write the address of the object, and then I'm going to write its pointer, P, Q, I don't know. I don't want to use the same P as in the slides, but I have some pointers, and then I will have the next object that I'm recording, right? So I will have records for each object that I modify. I'm going to log its previous values before I modify it, and then I'm going to mark it dirty, and no one else will need to record it. Yeah. I'm not doing reference counting here. I will do it when I work in the collector, but from the mutator point of view, the entire task has changed. Yeah. I just need to log the previous value of an object. So let me just, the moving from a pointer to an object, I just want to say that, so first off, why is it okay to do this? I want to say maybe you can say, I have an object and I just wrote to one of the pointer in it, and the other has not changed. So between the two collections, this one in snapshot K and in snapshot K plus one look at different things, but this one looks at the same thing at snapshot K and snapshot K plus one, and I don't need to update the reference counts. But this is okay. What I will do is I will decrement the reference for snapshot K and increment it for snapshot K plus one. I will not change the referenced value, the reference count. So it's okay to do. So first I want to say it's okay to log pointers that are not modified because I will not break any reference counts. But why do I do it? First, it's easier to have a dirty bit per object than per pointer. And the second thing is many times if I change a pointer of an object, I may change another pointer, or there is only one pointer. It's not usually a higher cost, and it's easier for me to write a dirty bit per object than per pointer. If I need to write it per pointer, I will need some space overhead for the pointers. So, but there are modern collectors who do it per pointer. It's possible. Okay, and I need to log here only non-null pointer fields. So I need to record the old values of pointers. I put it here. If it's null, I don't really need to put it here. If it's not pointers, I don't care about it. If it's an integer, I will not record the previous values. I only care about pointers. Okay, and finally, new objects. So new objects, they do not point to anything in the previous collection. So I will just put their address with no pointers. They will be dirty, so I will not need to copy them later. But I don't need to record any pointers for them because they pointed to nothing in the previous, they did not exist in the previous snapshot. So I don't need to do anything except for making sure they're dirty and written here. I will want to increment the reference count of the reference in the next snapshot. So I want them here. I want to go over this and increment the reference counts of the new reference, but there's nothing to decrement for the previous reference because they did not exist in the previous snapshot. Okay, so this is for new object. And what is the effect of this? So if you look at it, the number, so the fraction of stores that actually have to log the value because it is not dirty is very small. Like the highest is for Java C with 1/40, but you have some things that are really small. And so most of the time you just check a flag and go on with the assignment. So the write barrier is very, very fast. You don't have the problems of reference counting that had such a costly write barrier. You just have this barrier that usually just checks a pointer, and once in a while, with this very low probability, it has to copy the previous values of the object to the buffer. Okay, so the first thing is that you really significantly reduce the work of the reference counting. And the overhead of the write barrier is also dramatically reduced because you don't need to decrement a reference count and increment a reference count. You just need to check this flag and decide if to copy it or not. So there are two things. First of all, the number of, so if you look at it, like in the past, for each pointer modification, I had to do a decrement and increment for the previous and next value. Now, 1/269 of the cases, I will have to do a decrement and an increment, but for all the others, I will not do it. So I'm removing a lot, these telescopic series, I'm removing most, like the vast majority of reference count updates. So we both reduce the work of the reference count, and we also make the write barrier very short and efficient. And finally, like you said, now in the write barrier, I don't do reference counting, I just record the previous value. I will do reference counting when the collector kicks in and does its work once in a while. But in the write barrier, it just looks the same as the mark sweep. So now I don't have to do in the write barrier any synchronization because the task has changed. I'm now just using recording the previous value. I'm not doing reference count updates. So all these problems that we had have vanished. So I can use exactly the write barrier of the previous lecture, I will soon put it. And so here it is. This is the previous lecture right barrier. I remember I copy the reference, the values of the references. I check if it has not been copied yet. If it has not, then I log all these values and then I mark it as dirty. And we said that if we do that, we have exactly, we always have in the buffer the values of the previous snapshot. We have no problem. So if we have this write barrier, even if two threads are together accessing, changing this object, I will get a single view of the object, which is exactly as it was in the previous snapshot. And with that, I can work and modify the reference counts later and get updated reference counts for reclaiming those who have zero. So great. I have that. It's a different goal for this write barrier. For tracing, we needed to record previous values because we wanted to trace according to these values. Here, we want to record previous values so we can decrement the reference count. So it's a different goal. It's the same technique, but there is one thing that is different for when we do mark sweep, or wait, okay, no, it's not said here. It will be said, yes, for tracing, we wanted to trace through it. So when we're done with the marking phase, we can stop the write barrier. We don't need it anymore. We just need it for the tracing. In reference counting, it's a bit more expensive. We need to keep it running all the time because we want to know about all the pointers that are modified between two snapshots. So we cannot stop after a while running the write barrier. We need to keep on running it. Okay, so so let's look at the timeline, how it works. So we have a snapshot in which we take the buffers, we clear the dirty bit, and we update the reference count, and then we can collect, right? And then between collections, the program records all the previous pointers before they update pointers. And then in the next snapshot, again, we take the buffers with all the modified pointers, we clear the dirty bits, just that everything will start from scratch, and we update the reference counts and collect, right? Make sense? Okay. If we look closer, what we can do, we need to scan the roots. Remember, we don't have monitoring for local pointers. We get the completed buffers so that we know all the pointers that were changed. We erase the dirty bit, and actually, after that, we can let the threads go on working. So they can just resume, and we can work concurrently to decrement the values in all the buffers that we took. We need to increment the current values, the values that are here, which seems that we have to worry about if they change while we're working. Soon I'll get to that. But if I do the decrements and the increments, I can collect all the dead objects concurrently with the program. So I don't need to do it all when the program is stopped. The only thing that seems a bit maybe tricky is that I need the values here and I'm letting the program run. So maybe these values are modified and I don't have them anymore. What do you think? Yeah? They get new ones, yes. Right. Yes. So if something is changed here, then there are new buffers that tell me what the values were here. So I'm not going to steal these buffers, but I can look at them and I can see what the values were here and then increment the reference as they were here by either looking at the heap if it wasn't changed, or if it was changed, then I have buffers that telling me how it looked here. Looks reasonable? Okay. You're not sure? So should I say it again? Okay, let me say what? The problem and the solution. Okay. I need to, between these two snapshots, I need to get all the modified pointers for each of them. I have to decrement the count of the referent here and increment the count of the referent here. Now, what I want to do is just to get all these buffers, and I want to work on all the decrements and increments while the program is running so that I get a concurrent collector. Okay, but so to decrement values, I collected here the buffers that were accumulated here. I can look at them. I have the old values. I can decrement, easy decrement all the values, all the reference that were here. Now I have to get all the current values, the ON. Like I reduced the O0 was here, ON is here. The problem is that the pointer keeps on modifying. So maybe it's now ON plus 7 if I just read the heap. It's not the same ON that was here, right? But I must get the value here in order to increment each reference count. Next snapshot, I will have to do other things, right? I will have to increment the values. No. I must decrement O0's reference count and increment O1, ON reference count. So think that I had this, you remember this, this pointer that I'm seeing in the buffer, there is some pointer, and I need to find O0 and ON. And this is like snapshot K. This is where it pointed it in. It's not clear that it's unreachable, but but I just need to know. I have this pointer. I know it's written in the buffer that it pointed to O0 here. Now I can either just read it here. That's okay. But if I want to let the program continue running, then I'm not reading all these pointers here. I'm reading them while the program is running, and then I do all the increments. So I have lots of pointers like this, and I have lots of ONs like this, and I have to know all of them. I could read it when the program is stopped, just read it from the heap. This is the current snapshot. But if I let the program go on, then this pointer is going to keep on modifying, and I don't know what is ON anymore. And I need to find ON. ON is this pointer, what it referenced here. And but what I have is that buffers are keep on. I mean, the program keeps on writing when it first changes a pointer. So if this pointer that I need is changed after I let the program run, then the program would keep a copy for me in the new buffers. So now there are buffers of all the modified pointers from here till the next. And in these modified buffers, I will find my own pointer that I needed for the previous changes. I will find its old value, and its old value now is this snapshot. So if it hasn't been changed, I can just read it. It's the same as in the snapshot. If it has been changed, someone kept a copy for me on how it looked at snapshot K plus 1. Okay? Okay? Yeah, so I just need, for each of the pointers that I got that were changed here, I need its value here. I could read it here, but if I read all these pointers, the program has to wait for me to read. I don't do that. I let the program go on working. The program then changes my pointer. So if it doesn't change the pointer that I need, I could just read it whenever I get to it. But if it was modified, then I know I have these buffers that keep values from the snapshot. I could consult with them and see what it pointed to in snapshot K plus 1. Right, right. If I look at the heap, this could now point to ON plus 10, right? But I have buffers, and my buffers tell me how it was in snapshot K plus 1. Okay. Is this okay? Anybody wants me? I can explain again. Okay, so this just says it. It's what we explained. Unmodified buffers can be read from the heap, and modified buffers can be read from active buffers. Okay, cool. So again, we have this optimistic if that we had last time. We can also have it this time. We don't need it for correctness, but since most of the time objects that we meet are already dirty, if it's not dirty, we need to do this. But if it's already dirty, we can jump and just do the pointer modification. So this is just an optimistic if. It's not needed for correctness, but it's useful for efficiency. So cool. Okay. So the buffers. We talked in previous lecture about technical issues with these buffers, but each thread just uses a local buffer to log all its entries in, and the collector looks at the buffer when it just wants to find the value, or it can steal them during a snapshot, so it will know everything that was done until now and let the program work with new buffers. To find, how do you find an entry of a dirty object? So now suppose I have this problem really that I'm going in the time from snapshot k plus one, and now I need to find something, some pointer that was modified. I want to know how it looked in the previous snapshot. I need to find the buffer where its entry is in, and there I will find its value in the previous snapshot. So how will I find its buffer? What Yossi did, it's just used, instead of a dirty flag, it used a dirty pointer. So it's like we did last week. I just look at the pointer and I know where this entry is, and so I can easily find what its value was in the previous snapshot. Okay. Okay, cool. And now we have a concurrent collector. So we're fine with it, and we want to make it on the fly. And this sliding views methodology to go from concurrent to on the fly, we talked about it in Mark Suite because it was easier, but it was invented here for reference counting. And it's the same thing. I just need to snoop. So this is, if I wanted a snapshot, I just stop all the mutators and I scan the roots, I get the buffers, and I clear all the dirty bits, and then I let them go on. If I want to have okay, you know what? Let's talk about the concurrent collector first. If I do that, I scan the roots while it is stopped, and then I get the buffers and clear all dirty bits. It means that the write barrier starts from scratch, and everybody will tell me when anything is modified, it will give me the previous values as they were in the snapshot. So here I just need to decrement the reference count, like we said. For O0 decrement, for ON I increment the reference count, and then I can reclaim all objects that are not local. This is okay, and it's just I get accurate reference count for the snapshot after I update all the modified pointers, and progress. So if an object had a 0 reference count before the snapshot, then I will see that it has a 0 reference count and I will reclaim it. If it's not in a cycle, it must have a 0 reference count, either immediately or recursively through its parents that gets deleted. And the safety is just the same as the snapshot paradigm. If I have something that is unreachable, it's going to remain unreachable until the collector reclaims it. So we're okay, and therefore we get safety, we get progress. If we want to move to okay, so why do we? So pause times for the concurrent collector is for stopping all the threads, for cleaning all the dirty bits, and marking the roots of all the threads. And we would like to make it shorter. So that's not bad. Actually, you could work with it. It's not a long pause. But if you really want short pauses, then you want to really do each of it in a handshake, that each thread will stop in its own time and maybe mark its roots or start the write barrier or do these things. And so if you want to do that, you can use the sliding views. You remember the methodology said, if your collector looks at the heap between intervals T1 and T2, and everything that it sees is from a view that's between T1 and T2. And if you do snooping all of this time, record new objects that get new pointer and treat them as roots, then you're seeing something that has more pointers than a snapshot at T2. So if you're seeing this, then you know you will not lose any object. And okay, this is what it says. All this we did last time. Okay. So here is the right barrier that you will work. So you will do snooping throughout the time that you're taking the sliding view, and it will look like this. You stop each thread to initiate snooping, you stop each thread to steal the buffers and clear all dirty bits, then you stop each thread to scan the roots, and then you stop snooping and you can work with the sliding view. So and the same collector will work. I will not start proving it as we did last time. So, it's not a consistent snapshot, it's a sliding views. It's more complicated. You have to work on showing that it's correct. I will not show that all the pointers are red in the sliding views. It's similar arguments to what we had last time. So I'm going to skip it. I think each of you, if you were left in a deserted island and had to do it to get out of there, you would do it. So, but I will not do it now. So clearing the dirty bits, there are some issues that I'm skipping. So this is the first one, to show that all pointers are red in the interval where there is snooping. The second issue that I'm skipping is that I clear the dirty bits while the write barrier is working, right? So write barrier is all the time, is running. We cannot stop it. So if you look at it, then I am running these handshakes, and at some point I'm clearing the dirty bit. And when I'm clearing the dirty bits, the other threads are still running and changing. And so it's possible that a thread will record the value of P here. And after I clear the dirty bit of P, maybe the same thread or another thread will record the value of P later, all within the time between T1 and T2. So you will have two buffers entries with two different values because it's different here and here. This is a little bit more complicated than we had last time. The thing is that both of these views are between T1 and T2. So if you choose one and use it, it's fine. It's within the sliding view. So I need to claim it more seriously. I'm skipping it. So clearing of the dirty bit is something that needs to be addressed. So even if I double log like last time with the same value, if I have two threads that have entries for the same pointer and they're the same, I need to only one time decrement and increment the reference count for that. So I have to be sure that I don't do it twice, because if I, for one change of a pointer, I decrement twice and increment twice, my reference counts will not be true, will not be correct. And so I need to only use one entry for each object. Now, as Yossi did it, he had an object with a pointer to the entry. If you do that, it's very easy to just use one of the copies because you use the copy. So this address points to the object and you check that the object points back to the same address. If you have another copy that's with the same view of the same object, the pointer in the object will not point to both of them. It will just point to one. And so you can find just one of the copies of the entries and just use it. So you don't want to update the reference counts more than once because it will destroy the reference count. And you can use it, and you have to, either by this method or another method, you have to make sure for each pointer, for each object, you just use one entry. Okay? And I will not discuss correctness. All of this I skip because I've done it last time and it's technical details that I don't think are very important now. Okay, so cycle collection, what Yossi did. So you could use tracing like mark sweep once in a while to remove all the cycles that you could not reclaim by reference counting. The algorithm that we studied in the previous lecture easily matches these reference count collectors because we have the same write barrier. So they could just once in a while run reference counting, once in a while run mark sweep. You could work with them together. You could alternatively use a cycle collection that we'll talk about next week. But Yossi used the mark sweep that we talked about last semester, last lecture. So let's see a bit about how it works. So first of all, if you compare it to a Stop the World collector, it's not a fair game, but you can see that the Stop the World takes a few hundred milliseconds, and this one takes just a couple of milliseconds. So this just shows that on the fly gives you a lot shorter pauses than Stop the World, which makes sense. Now, if you compare it, what you have here is in the system where Yossi implemented his collector, his reference counting collector, there was another reference counting concurrent collector. This was the one by the IBM people, the Bacon et al. That I talked about, just because just before update coalescing was found, this method of coalescing all the reference count update was found. This collector was the state of the art as it was there. And what you can see is that it took maybe 50% more time than Yossi's collector. What you see here, we didn't talk about spec JBB last time because we didn't have time. What you see here is, first of all, there are eight levels of running the application, where each of these levels is just imitating some. It's like a benchmark that imitates a commercial company that has warehouses, and it has several warehouses. Here it has 8 warehouses, and here it has 1. And there is a thread handling each warehouse. So with 8 warehouses, you have 8 threads. With 1 warehouse, you have 1 thread. And the heap, the usage of the heap also increases because each warehouse uses some space in the heap. So when you take, this is the most busy application. It takes 8 threads and the largest space consumption. This is the blue one, and you see it here. And the one that uses the least resources is JBB1, which is just the lower one. And so what you can see, if you don't need a lot of garbage collection work, then you basically, this is 1, so you have 5% loss by using the old collector. But if you need a lot of work and say you take a reasonable heap size, then you lose between 30 to 60% by using the old collector. So this is a nice advantage to throughput. And the reason is you just lose a lot of the reference count updates because you're using this update coalescing. You don't need to do all the reference count updates in the middle. You coalesce all of them. And also you don't have an atomic, you don't have a compare and swap or a lock in the write barrier. So you're doing a lot faster. So this is what you see here. old reference counting against the new reference counting. Um, I'm skipping another smaller benchmark, which is around the same. Now, if you look at the stop the world collector against the concurrent collector, the on-the-fly collector, here you see a loss of throughput, and it's between, I don't know, 2% to 17%, and basically a 10% loss if you move to on-the-fly collectors from stop the world. So you win in the short pauses, but you lose in the throughput, which is fine. It makes sense. So this is this for the spec JBB. I'll skip the smaller benchmarks. And here is a comparison of the algorithm we learned last week with mark sweep to the algorithm that does reference counting. And what you see here is that the mark sweep wins when the heap is large. Okay, so it wins by maybe 3 to 7% when the heap is large, and you can run the collection once in a while. If the heap gets tight and you need to run lots of collections, then reference counting is starting to win by a large factor. If you really have 8 threads and really 8 warehouses, and you really need a lot of the heap, and you don't, and you're tight, and you have to do a lot of collections, then you can lose, half of the time because you just don't make it to finish the marking until you need space. Even though you do it concurrently, you don't make it, and then all the threads start to wait until you finish in order to get space. Then you really lose half of your time on garbage collection. So this is not the final word, by the way. There are modern collectors that use these methods and get it down to almost the same. Sometimes reference counting is doing better even when the heap is not tight. We'll talk about it next week. What else? That's it. So this Lebanoni reference counting properties is you use the update coalescing, then you remove lots of the reference counts updates from the execution. The write barrier is light. You don't need compare and swap or locking in order to do the modifications. And on the fly, you get low pauses. You use the snooping and sliding views. You become on the fly, and you have very short pauses. And if you don't want to use the concurrent one and you want to use the on the fly, it's not simple. You remember that I skipped a few items because they were more complicated for discussing thoroughly in class. So this is this, and to summarize reference counting, we've seen some simple adjustments to the reference counting. We moved to deferred reference counting, not to monitor the roots, which is crucial in order to get performance. We talked about the problems with concurrency and also with the overhead. And we talked about Deterville, who did this locking for maintaining concurrency. And Bacon et al., we didn't really talk about it seriously, but we just mentioned it and compared results, evaluation in the end. And we talked about update coalescing, about how to do reference count concurrently and on the fly. That's it. Questions generally? Okay. Okay. I don't think I will start talking about the rest of the slides. We'll close here and meet next week. Cool? Okay.